Welcome to our comprehensive guide on species distribution modeling, calibration, evaluation, and ensemble modeling. In this video, we'll journey through the essential steps and best practices for predicting species distributions using advanced modeling techniques. Whether you're new to ecological modeling or looking to refine your approach, this series will provide you with the foundational knowledge and practical insights needed to succeed. We'll start by exploring the basics of data formatting and move through the intricacies of model calibration, validation, and ensemble strategies. Let's dive in and discover how to turn raw data into actionable ecological insights. Species distribution modeling follows a structured workflow. It begins with data formatting, where we organize presence and absence records alongside environmental variables. Next, we generate pseudo-absences if real absences are unavailable, ensuring a balanced dataset. Cross-validation is then used to partition data, allowing us to assess model performance reliably. Throughout this process, we consider various modeling options and tune parameters to optimize results. Finally, we evaluate model outputs and, if appropriate, combine multiple models into an ensemble for robust predictions. This workflow ensures that each step builds logically on the last, leading to scientifically sound conclusions. Proper data formatting is the foundation of any successful modeling project. We start by collecting species occurrence data, which may include both presences and absences. Environmental variables such as temperature, precipitation, or land cover are then linked to each record. It's crucial to ensure that data are clean, consistent, and free from errors. When only presence data are available, we avoid mixing them with real absences and instead generate pseudo-absences to create a balanced dataset. This careful preparation sets the stage for reliable model training and evaluation, minimizing bias and maximizing predictive power. Many ecological studies, true absence data are hard to come by. To address this, we use pseudo-absences, locations where the species is assumed absent based on sampling strategies. These can be generated randomly within a geographic disk or using environmental criteria to ensure the niche is well sampled. The choice of pseudo-absence strategy can influence model outcomes, so it's important to match the method to your ecological question and data availability. By thoughtfully generating pseudo-absences, we create a dataset that allows for more accurate and meaningful model predictions. Cross-validation is a critical step in model evaluation. By partitioning the data into training and validation sets, we can assess how well our model generalizes to new unseen data. Common approaches include simple calibration validation splits, k-fold cross-validation, and stratified partitioning based on spatial or environmental criteria. Each method has its strengths, and the choice depends on the dataset size and structure. Repeating cross-validation multiple times helps to reduce variance and provides a more robust estimate of model performance. This process ensures that our models are not just fitting noise but capturing real ecological patterns. Species distribution modeling offers a variety of modeling options. Researchers can choose from single models like generalized linear models, GLM, random forest RF, or more complex machine learning algorithms. Each model type has its own assumptions, strengths, and limitations. The choice of model depends on the research question, data characteristics, and computational resources. Exploring multiple models allows us to compare their performance and select the most appropriate approach. This flexibility is key to addressing diverse ecological questions and ensuring that our modeling efforts yield reliable and interpretable results. Tuning is the process of optimizing model parameters to achieve the best predictive performance. This can involve adjusting settings like the number of trees in a random forest or the regularization strength in a GLM. Automated tools such as the caret package in R can test a range of parameter values and select those that maximize evaluation metrics like TSS or ROC. Proper tuning helps prevent overfitting and ensures that the model captures the underlying ecological processes rather than noise. It's a crucial step for building robust and generalizable models. Once models are trained, evaluating their performance is essential. Common metrics include the true skill statistic TSS, area under the curve AUC, and confusion matrix components like true positives and false negatives. These metrics provide insights into how well the model distinguishes between presences and absences. Evaluation often requires transforming continuous predictions into binary outcomes using optimized thresholds. By systematically assessing model performance, we can identify strengths and weaknesses, compare different models, and select the best approach for our ecological question. Ensemble modeling combines predictions from multiple models to improve overall accuracy and robustness. By leveraging the strengths of different algorithms, ensembles can reduce individual model biases and variance. Common ensemble techniques include averaging predictions, majority voting, or weighting models based on their performance. Ensembles are particularly useful when single models show varying results, as they provide a consensus prediction that is often more reliable. This approach is widely used in ecological modeling to enhance predictive power and account for model uncertainty. Understanding which environmental variables drive species distributions is a key goal of modeling. Variable importance can be assessed by comparing model predictions with and without each variable, often using Pearson correlation or permutation methods. This analysis reveals which factors most strongly influence the probability of presence, guiding conservation and management decisions. Comparing variable importance across models also highlights consistent drivers and potential sources of uncertainty. By focusing on the most influential variables, we can streamline models and improve interpretability. Visualizing model outputs is crucial for interpreting results and communicating findings. Graphical representations can include maps of predicted distributions, plots of variable importance, and evaluation metric charts. These visuals help identify spatial patterns, assess model fit, and compare different modeling approaches. Effective visualization makes complex results accessible to a broader audience, including stakeholders and decision makers. By integrating clear graphics into our workflow, we enhance both the scientific rigor and practical impact of our modeling efforts. Presence-absence data forms the backbone of many species distribution models. These datasets record where a species has been observed, presence, and where it has not absence. Accurate presence-absence data allows for robust statistical analysis and model calibration. However, collecting true absences can be challenging, leading to the use of pseudo-absences. Ensuring that presence and absence records are representative and unbiased is essential for reliable modeling. This careful attention to data quality underpins all subsequent modeling steps. Some cases only presence data are available. Presence-only modeling requires special considerations to avoid bias. It's important not to mix presence-only data with real absences, as this can distort model predictions. Instead, pseudo-absences or background points are generated to provide a contrast for modeling. Sampling strategies for pseudo-absences should be carefully chosen to reflect the ecological and geographic context. By understanding the limitations and strengths of presence-only data, we can still derive meaningful insights from incomplete datasets. Random sampling is a common method for generating pseudo-absences in presence-only datasets. This approach involves selecting random locations where the species has not been observed, under the assumption that these represent true absences. However, random sampling can introduce bias if the sampling is not exhaustive or if certain areas are underrepresented. To mitigate this, researchers may use stratified or targeted sampling strategy. The goal is to create a set of pseudo-absences that accurately reflects the range of environmental conditions in the study area. Beyond random sampling, disk and SRE surface range envelope methods offer alternative approaches for generating pseudo-absences. Disk sampling focuses on geographic proximity, ensuring that the niche is well sampled spatially. SRE sampling, on the other hand, targets environmental space, selecting pseudo-absences that represent the full range of environmental conditions. Both methods aim to improve the representativeness of pseudo-absences and reduce bias. Choosing the right method depends on the study's goals and the nature of the available data. Calibration and validation are essential for assessing model performance. A simple split divides the data into calibration training and validation testing sets. This process is often repeated multiple times to ensure robust results. By evaluating model predictions on independent validation data, we can gauge how well the model generalizes beyond the training set. This step helps identify overfitting and ensures that the model captures genuine ecological patterns rather than artifacts of the data. A-fold cross-validation is a popular method for partitioning data into multiple subsets, or folds. Each fold serves as a validation set while the remaining folds are used for training. This process is repeated so that each fold is used for validation once. K-fold cross-validation provides a comprehensive assessment of model performance, reducing the impact of random variation in the data split. It's especially useful for small datasets, where maximizing the use of available data is critical. Stratified partitioning divides data based on specific criteria, such as spatial coordinates or environmental variables. This ensures that each subset is representative of the overall dataset, reducing bias and improving model reliability. User-defined splits offer even greater flexibility, allowing researchers to tailor the partitioning strategy to their unique study design. These advanced splitting methods are particularly valuable in complex ecological landscapes where simple random splits may not capture important patterns. Maintaining a balanced prevalence of presences and absences in each data subset is crucial for model stability. For example, keeping a 25% prevalence of presences ensures that the model is not biased toward predicting absences. This balance can be achieved through careful sampling and partitioning strategies. Balanced datasets lead to more reliable evaluation metrics and improve the interpretability of model results. It's a simple yet powerful step in the modeling workflow. Wide range of model types are available for species distribution modeling, including 14 single models coded in various R packages and external software. Each model type offers unique features and is suited to different ecological questions. The Biomod 2 package, for example, integrates multiple modeling approaches and allows for flexible parameter tuning. By leveraging different software tools, researchers can compare model outputs and select the most appropriate method for their study. Model parameters can be set to default values, extracted from functions, or customized by the user. Default parameters provide a starting point, but custom settings allow for fine-tuning based on the specific dataset and research goals. The Biomod 2 team also offers redefined parameters, known as Big Boss settings, which are optimized for common modeling scenarios. By experimenting with different parameter configurations, researchers can identify the best setup for their model. Advanced users can define their own model parameters, tailoring the modeling process to their unique needs. For example, neural network settings like size, decay, and maximum iterations can be specified directly. Additionally, models can be tuned using automated tools that test a range of parameters and select the best based on evaluation metrics. This level of customization ensures that models are both flexible and optimized for performance, accommodating a wide variety of ecological questions. Single models, such as GLM or RF, are implemented across multiple data partitions and runs. Each combination of pseudo-absence, run, and model type generates a unique model instance. This comprehensive approach allows for detailed comparison of model performance across different scenarios. By systematically varying model inputs and settings, researchers can identify the most robust and reliable modeling strategies for their species of interest. Most evaluation metrics, except ROC, require binary predictions. This involves transforming continuous model outputs into presence or absence using a threshold. The optimal threshold is selected by maximizing the chosen evaluation metric. By systematically testing a range of thresholds, we ensure that the binary transformation accurately reflects model performance. This step is crucial for interpreting results and comparing models on a common scale. Variable importance can be compared between models by analyzing the impact of each variable on model predictions. Techniques such as randomizing one variable at a time and measuring changes in prediction accuracy help identify key drivers. Pearson correlation is often used to quantify the relationship between normal and randomized predictions. This analysis provides valuable insights into the ecological processes shaping species distributions and highlights variables that warrant further investigation. Exploring the results of single models involves analyzing predictions, evaluation metrics, and variable importance for each model instance. Visualization tools help identify patterns and inconsistencies across models, runs, and data partitions. By systematically reviewing these outputs, researchers can refine their modeling approach and select the most reliable models for further analysis or ensemble construction. This iterative process is key to building robust ecological models. Concept of evaluation space allows us to visualize the consistency of evaluation metrics between models. By plotting metrics such as TSS or AUC for different models and runs, we can assess their agreement and identify outliers. This graphical approach provides a holistic view of model performance, highlighting areas of strength and potential improvement. It's a powerful tool for comparing models and ensuring that conclusions are based on consistent, reliable results. More classical view of model metrics involves summarizing evaluation results in tables or bar charts. This approach makes it easy to compare models side by side and identify those with the highest performance. By exploring different levels of data subsets, such as runs or pseudo-absences, we gain a deeper understanding of model variability. This comprehensive analysis supports informed decision-making and model selection. Pairing the consistency of variable importance and evaluation metrics across different models and model types is essential for robust ecological inference. Visualization tools can highlight agreement or discrepancies between models, guiding further investigation. Consistent results across models increase confidence in the findings, while discrepancies may indicate areas for further research or model refinement. This step ensures that our conclusions are well supported and scientifically sound. Partial dependence plots help us understand the effect of each variable along its gradient on the probability of species presence. By visualizing how predicted probabilities change as a function of a single variable, we gain insights into ecological relationships and model behavior. These plots also allow us to compare the consistency of variable effects across different models, enhancing our understanding of species-environment interaction. Projecting single models onto new environmental data allows us to predict species distributions under different scenarios, such as future climate conditions. This step involves applying trained models to novel data and interpreting the resulting predictions. By comparing projections from multiple models, we can assess the robustness of our forecasts and identify areas of agreement or uncertainty. This forward-looking approach is vital for conservation planning and ecological forecasting. Projecting models, it's often necessary to transform continuous predictions into binary outcomes. This allows for clear interpretation of presence and absence under new conditions. The choice of threshold for binary transformation should be consistent with the evaluation step, ensuring comparability across models and scenarios. This process supports clear communication of results and facilitates decision-making in applied context. Building ensemble models involves combining predictions from multiple single models. This can be done through averaging, majority voting, or weighted approaches based on model performance. Ensembles help to mitigate individual model biases and provide more stable predictions. By systematically constructing and evaluating ensembles, we can enhance the reliability and interpretability of species distribution forecasts. Ensemble models are evaluated using the same metrics as single models, such as TSS, AUC, and confusion matrices. By comparing ensemble performance to individual models, we can assess the added value of combining predictions. Ensembles often show improved accuracy and robustness, especially in complex or uncertain ecological contexts. This step confirms the benefits of ensemble modeling and guides the selection of the best ensemble strategy. Assessing variable importance within ensemble models provides insights into the most influential environmental drivers across all models. By aggregating variable importance scores, we can identify consistent patterns and reduce uncertainty. This analysis supports targeted conservation actions and enhances our understanding of species-environment relationships. It's a powerful way to synthesize information from multiple modeling approaches. Ensemble models can be used to analyze changes in species range under different scenarios, such as climate change or habitat alteration. By comparing predicted distributions across time or conditions, we can quantify range expansions, contractions, or shifts. This information is critical for conservation planning, helping to identify vulnerable species and prioritize management actions. Range change analysis transforms model outputs into actionable ecological insight. Visualizing ensemble model outputs helps communicate complex results to diverse audiences. Maps of predicted distributions, range change diagrams, and variable importance plots make findings accessible and actionable. Effective graphics highlight key patterns and support evidence-based decision-making. By integrating visualization into the ensemble modeling workflow, we enhance both scientific understanding and practical impact. Successful species distribution modeling relies on best practices at every step. This includes careful data formatting, thoughtful selection of pseudo-absences, rigorous cross-validation, and thorough model evaluation. Tuning parameters and comparing multiple models further enhance reliability. Ensemble modeling and clear visualization synthesize results and support decision-making. By following these best practices, researchers can produce robust, interpretable, and actionable ecological insights. Modeling species distributions comes with challenges, such as biased sampling, overfitting, and misinterpretation of results. Common pitfalls include mixing presence only with true absence data, neglecting to tune parameters, or relying on a single model. Solutions involve rigorous data preparation, cross-validation, and ensemble modeling. By anticipating and addressing these challenges, researchers can avoid errors and produce more reliable models. Ultimate goal of species distribution modeling is to inform conservation and management decisions. By integrating model results with ecological knowledge and stakeholder input, we can prioritize actions and allocate resources effectively. Clear communication of findings, supported by robust modeling and visualization, ensures that scientific insights translate into real-world impact. This integration is the final step in the modeling workflow, closing the loop between data, analysis, and action. Species distribution modeling is a rapidly evolving field. Advances in machine learning, remote sensing, and big data are opening new possibilities for more accurate and scalable models. Integrating genetic, behavioral, and interaction data can further refine predictions. As computational power grows, ensemble and hierarchical modeling approaches will become increasingly accessible. Staying abreast of these developments ensures that researchers can leverage the latest tools and techniques for ecological forecasting. Let's recap the key concepts covered in this video. We explored the full workflow of species distribution modeling, from data formatting and pseudo-absence generation to model calibration, evaluation, and ensemble construction. We discussed the importance of cross-validation, parameter tuning, and variable importance analysis. Visualization and integration of results were highlighted as essential for effective communication and decision-making. By mastering these concepts, you're well-equipped to tackle complex ecological modeling challenges. Species distribution models have a wide range of practical applications. They inform conservation planning, guide habitat restoration, and support biodiversity monitoring. Models can predict the impacts of climate change, identify invasive species risks, and prioritize areas for protection. By translating complex data into actionable insights, species distribution modeling plays a vital role in sustaining ecosystems and supporting policy decisions. Deepen your understanding of species distribution modeling, explore additional resources such as online tutorials, scientific publications, and open-source software documentation. Engaging with the modeling community through forums and workshops can provide valuable support and inspiration. Continuous learning and collaboration are key to advancing your skills and staying current in this dynamic field. Thank you for joining us on this journey through species distribution modeling. By mastering the workflow from data preparation to ensemble modeling, you're equipped to make meaningful contributions to ecological research and conservation. Continue exploring, experimenting, and collaborating to push the boundaries of what's possible in ecological modeling. Stay curious and keep building your expertise in this exciting and impactful field.